So this is really work that Mike Ortega did together with us while I was still at York University, but Mike can't be here today, so I'm presenting in his stead. So we're talking about orbiting, and most of you know this from, say, SketchUp or other 3D software packages where you rotate around an object. And in a minute or so, I'll actually be I'll be orbiting around this podium here so to see some of the ideas, but we'll get there in a moment. So as long as the object is roughly spherical or it has a shape that is easily described by a spherical object, it's fairly easy to rotate around an object because all you need to do is to rotate around the center. If the object is longer, like this object here, then you have two choices. You can either stay relative to the position that you were and rotate into the object, which is not very good, or you make the radius larger, and then you have the problem that the object gets much further and comes much closer with the orbiting. So in this case, it's much better if you basically try to stay roughly at the same distance away from an object, and you basically adapt a path around the object of the shape of the object itself. The questions don't stop there, because one of the things that you realize is, what if it's not a single object, but a collection of objects? In this case, at this distance of the camera, the best choice might still be to rotate around the group of the objects as one object, basically, as an virtual object. One of the things that very few people talk about is that if you rotate around an object, one of the issues that you run into is that you don't look behind yourself. So if I'm rotating around something over here, I can easily crash into the podium because I don't see it. And in fact, because your view looks like this, you won't be able to see the podium. And then so you tend to orbit into other objects. Now, it depends on the rendering method and what you use. Either you see the inside of the object, which is highly confusing, or you see something else that's weird. If you're lucky, it's backface calling and you don't see the object, but then the problem is if the object just comes in like this, oops, wait, what happened? And we all know that novice users get very confused by this. Just ask anybody who's learning to play a computer game. There have been solutions for this in the past. I don't have the time to review all of it. I'm just going to pick HoverCam here as the most prominent method in this field. The design of it is basically to keep the camera at a constant distance to the object. And one of the key features of this method is that it also looks precisely at the closest surface point. So you see this in the bottom right. On the right-hand side, the camera on the left side looks at the corner, even though it's already rotated a bit further. And we'll talk a little bit more about this in a second. So there's several limitations that HoverCam has. If you rotate around an object that is tessellated, it will stop on edges. So if you look at the bottom left corner, there's a little visualization of where the camera looks at any given point along this path, and you can see that this is far from smooth. And the problem is really it depends on the object. It depends on the tessellation of the object, and you will see examples of this live in video in a minute. The camera also stops completely inside a concavity, so if you get into a concavity, the camera will basically start rotating and then continue moving, right? And so you have this odd start-stop behavior that the position of the camera stops, but the rotation of the camera starts, right? And so this leads to some visual artifacts. If you use complex surfaces, such as this mesh surface, this mesh ball down there, what happens is because of the requirement of HoverCam to have the camera always look at the closest surface point, the camera will actually vary not only horizontally, but also vertically. So you have a path that's going to jitter up and down. And that's not exactly as intended. And finally, it's really targeted at only orbiting around a single object. So HoverCam overall has a high variability in the optical flow, and worse yet, from an interaction point of view, maps interactions inconsistently. And it depends, for example, on the object. So to show you this in a video, these jitters in there are actually HoverCam. This is not because of any video artifacts or anything like this. This is as HoverCam rotates around the object. So in the original paper of SHOCam, they suggested to smooth the object geometry, or either in geometry space or in image space, and this is a potential solution, but again, it's dependent on the objects, really, so it's not really a general solution. So I'm presenting smooth SHOCam, which is designed to address these issues by reducing the variability in camera motion and viewpoint direction, have a more consistent interaction mapping, and also I present several solutions for orbiting around multiple objects. So in a nutshell, here's a visual comparison between the paths of the camera as well as the view directions of SHOCam and SHOCam around this star lollipop object that we use to evaluate some of the things. You can see this in interactive behaviors. And the bottom one is the SHOCam, the top one is SHOCam. So how do we do this? The basic concept is that instead of using the cameras directly, we actually interpolate from a set of pre-computed cameras. So on this slide, you see a set of 3x4 cameras that we used with these light blue view directions visualized here. And on this manifold, from this manifold, we interpolate the directions of the final cameras. So in the following couple slides, I will talk about how we compute these grid cameras, this set of cameras that we interpolate from. And it's fairly basic. We basically walk along the surface by looking at the closest feature and walking parallel to this feature. So if I'm here in front of this podium, I will walk in this portion. I will walk precisely parallel to this edge of the podium, right? As soon as I reach the edge of the podium, of course, I'll rotate and try to keep this my closest point. As we move around here, we have, of course, the problem, depending on which direction we move, we actually have to adjust our distance. So say I come around this corner here, and my view direction, my movement direction is this way. To keep the distance, I actually have to move closer, right? And so how do you discover that? At each step in the algorithm, you do a computation of the closest feature that you find in the environment, and then adjust your distance accordingly. So there's an iterative algorithm, and we basically try to make sure that the spacing between two cameras in this camera set is larger than a distance. This also works in concavities, where you now get into the situation that you get too close to things, and so you actually have to back off and then keep moving in it. So in this case, if you would just continue straight on with the top left, you would get too close, so you actually can't move that far. You have to keep sliding along the new wall against the top wall here. And that, of course, doesn't allow you to move the required movement distance, so you have to keep iterating until you do this, until you reach a sufficient distance from the previous camera. We use the sufficient distance, the criterion of a sufficient distance from the previous camera to guarantee that our interpolation has decent output at the end. The position and the orientation of the cameras is then interpolated from this set, where we use Catmull-Rom interpolation for the positions and Bézier for interpolation for orientation. Also, as we move, we have to continuously update the camera set, because every time we basically run out of cameras, we have to compute the new strip of cameras. And we adapt to the movement direction of the viewer, depending if the mover is moving predominantly horizontal or predominantly vertical, and use a different set of cameras. And there's an interesting design decision about this that I will discuss if I have time at the end. In terms of complexity, you would think that we do these computations of the closest distance at every step for the camera set, and yes, that costs time. We point out that we can parallelize some of that because we have to compute the whole set of them. And one of the other things is that we amortize basically this computation over the interpolation when the camera is actually moving. Right? So because we compute the camera set only when we have moved far enough, so it's basically an amortization process. So you can see here in this example how the method behaves when you move, in this case, horizontal and then vertical. And how the system switches, and you can see how it switches between the two different camera sets depending on the direction of the movement. So we evaluated this, and in different, with different criteria, both in terms of an objective evaluation of the quality in terms of optical flow, how much computations we need, and what users say about the method. So the first thing is that we basically computed the changes in the viewpoint direction and the changes in the viewpoint velocity, and the green line is HoverCam, and the blue line is SHOCam. As you can see, with the viewpoint velocity, we have a much more constant velocity. The camera stops for 30% of all frames around the 3 bunnies here with HoverCam, so that's not desirable. You can see this actually in regions such as the little fan triangles at the top left, top right, and in the bottom center. There's these points where the viewpoint basically temporarily stops for a while. One of the interesting things that we discovered when we tried this, you see that the blue lines in the bottom of the graphs are actually shorter than the paths for HoverCam, because due to the interpolation and because of the fact that the camera doesn't stop, you actually need fewer steps to rotate around the whole object once with the same mapping. In terms of closest point computations, HoverCam needs to do a closest point computation for every camera, for every frame. Whereas we amortize across the frames. And you can see this comparison in this graph, that for pretty much every object we have less computations. And the frame rates, the final frame rates are comparable. There's actually one thing that we can vary in our method. The top 3 are different variations of SHOCam, whereas the bottom one is HoverCam. We have, depending on the distance, so you see that we plot here different paths depending on different distances from the object here. That's going across to the slide to the right. But by varying essentially the distance, how far we want to be from the object, and the distance between cameras in the camera set, we can generate different families of camera paths. So you see that the bottom alternative, where we get a behavior that's somewhat close to HoverCam but doesn't have the problem that camera stops. So in a sense, this is a generalization of HoverCam, or an improvement over HoverCam right there. We evaluated this in a user study with 14 participants. HoverCam versus SHOCam, and had a couple of tasks where we first had them just observe basically the method orbiting on its own, and then several free orbiting sessions. All people noticed, and actually without prompting, complained about the sudden jumps and this jakiness of HoverCam, and all but 2 preferred SHOCam in all conditions. It was interesting because we actually got also comments about the unpredictable behavior of HoverCam, which is exactly towards that point that it's a better SHOCam has a better interaction mapping. So one of the extensions of SHOCam, or one of the parts of SHOCam that we did not evaluate, is the part about moving between objects, because I talked about this in the very beginning, where you remember the red sphere where you orbit into if you're not careful. So what we do in SHOCam is if there's an object behind the viewer, we actually adapt the distance so that the viewer keeps the orbited object as the closest object. Now, this is actually an interesting design decision here, because you could argue that, well, I could orbit until my back is basically to the wall. Right? I could orbit right up onto the wall. And as long as the wall is flat, that's not a bad idea. But if the wall has spikes, the distance to the wall will change, and then you have really weird orbiting behavior, because we will basically trace a path along the spikes along the wall. And so that's not desirable. So for this reason, we decided to, pun intended, implement a middle ground between the methods, where we keep the camera in the middle between the 2 objects. So in this image, you see a path where we rotate between the bunnies here around the middle bunny. And you could, the black bars are actually a visualization of the initial distance. And you can see that the camera goes closer and actually slows down between the bunnies. And then as soon as there's enough space, speeds up again. Another problem in orbiting is that you orbit around a big object, say the Earth, and it has satellites. Yes, you can do that. It's not a problem. But if you're orbiting around an object as large as the Earth, you might as well also orbit around the satellites at the same time. And so we actually look up and down in the scene hierarchy to identify an appropriately sized bounding box proportional to the right distance from the viewer. And so in this video clip here, sorry, that should be playing, you see how SHOCam works in a multi-object scene at the top, and at the bottom you see how it orbits around multiple objects, in this case, basically an Earth and a Moon. So I'll just leave the conclusions, actually. I'll just leave the final video up and be open for questions.
Hi, I have a few questions. First question is the orbiting path pre-computed, or is it computed on the fly?
On the fly.
Okay. How do you decide whether you're going to orbit it as a group or orbit as a blocker? Or
Excellent question. I did not have time to explain that in sufficient detail. I realize I had to cut it short a little bit there. So conceptually speaking, okay, when you go far away, and the object gets small on the screen, as soon as it goes below a certain threshold, we basically orbit around the larger group. Okay? When you get closer and the object gets large on the screen, we do the opposite to go lower in the hierarchy, and we just use the object that's closest to the center of the screen as the object to orbit around. Okay?
Hi, I'm Rufi from University of Maryland, College Park. I have a motivation question. I'm wondering, how did you come up with the smart idea? And is there any practical problem you are solving when thinking up this idea?
Sure. I mean, the problem that we observed, I mean, is exactly orbiting around such objects. And when we were actually looking at, we were actually discussing an elongated object and loaded in a SketchUp and started orbiting around it and noticed, well, no, this doesn't look so good, right? Okay. And so we started looking in the literature and said, what can we do? And HoverCam is clearly one of the main parts of the previous work here. And so then we noticed the problems and went from there, right?
Yeah. And my second question is there a way to recommend the best view for users using your algorithm? For example, you provide the best view for users with the most convex part.
Right. So there are methods to compute what you would call a best view, a single best view of an object, yeah. Right? The problem with that is that gives you one view. And okay. there are other methods that compute one image and then give you the second best view relative to that. So basically give you a series of snapshots that typically either viewpoint entropy based or other methods exist in this space. However, it's not that's not an interactive method.
Yeah.
Right?
Yeah.
Huh?
Okay, thank you very much.
How do you compute the closest distance?
Okay,
I mean, I'm asking specifically because when you look at the car and the dragon, sometimes you're missing the feet. So, like, are you always computing it in a plane?
Thank you. That actually, I promised that I would talk about that briefly. So there's multiple ways to do this. One, the naive way is to do it only, say, if I'm moving horizontally, is to compute only horizontal distances, right? Yet, say, if I orbit here and suddenly this microphone becomes my closest point, you would take that into account. So you actually have to take all the directions into account, okay? So in the implementation that we used here, we used raycasting to do that, but you could equally well use a frame buffer. Both of them would work equally well, okay?